programming, and then it went to where we ended with. But to clarify, a big friendly giant, it's definitely a subset of monster, right? So
That's the takeaway, yeah.
anyway, let's talk about oscillators today. So what we already did in that application, we talked about those relaxation oscillators, and those were a type of multivibrator. So, multivibrator and relaxation oscillator. So the fact that these relaxation oscillators are multivibrators the multivibrators have two stable states, two possible states. So the best you can get with this relaxation oscillator is a square wave. So you can get an oscillator, but you're restricted pulses like that. You could do some things like you could definitely change the duty cycle of the pulses, like on less than it is, and it is on less than it is off. But you're stuck with the square wave. Not that those aren't useful. There's a whole lot of stuff that multivibrators are crazy useful for, and they're not something that ignores. It's just like very useful general tool. And one thing that we'll talk about on Wednesday is a simplified way to build multivibrators using a single integrated circuit. What would be even better to have in square wave is some kind of sine wave. The sine or cosine wave we're going to get from a harmonic oscillator. So what I want to focus on today is how do we generate that? And there's really going to be three ingredients we need for this type of oscillator. You need some kind of oscillatory element. So this is like the basic thing in your circuit that's going to provide the oscillator. Like the C. So this is going to be like the base thing that can generate a sinusoidal wave. But whatever is generating this sort of oscillatory bit, that's going to take energy to do that. So this will continuously lose energy. So we're going to need to amplify that a little bit. And the signal that we need to amplify, so now we're amplifying the AC signal. The sure we amplify in phase. So we're going to need some kind of positive feedback to get this in phase amplification. Like if you're pushing a kid on a swing, push at the exact same frequency they're swinging at. Our amplified signal has to be matched up with what we're feeding back to it. So we're going to need some kind of positive feedback. So all three of these things are ingredients for getting some kind of harmonic oscillator. And the reason it's called a harmonic oscillator, obviously, getting the sines and cosines out that are harmonic functions. The reason that we're getting these nice sines and cosines out is that what we're essentially solving is some sort of equation that looks like d2i squared plus some constant times current is equal to 0. So we're just solving a harmonic oscillator differential. I'm going to come back to these three ingredients in a second. So I want to talk real quick about circuits. This is a term you see a lot in electronics, especially with oscillators. And for me, it took way longer than I had wanted to figure out what was meant by a circuit. So I wanted to start with there, because this is going to provide the basis for a lot of oscillator circuits. So this tank circuit is some kind of inductor capacitor circuit or inductor capacitor resistor. And I want to just remember how inductors and capacitors behave as far as frequency is concerned and the reactance. So the reactance was frequency dependent resistance. That's what you should think of reactance. For an inductor, low frequencies, it looks like a short circuit. For high frequencies, it acts like an open. So low frequencies, an inductor has a low resistance. It's just a piece of wire. Remember the inductance symbol? Looks like a coil of wire. That's what it is, and it's a piece of wire. So for low frequencies, this just looks just like a piece of wire. It's going to have really low distance. If you're at high frequencies, the inductor is going to look more like, it's going to have a high resistance. The cool thing about the capacitors, and this is basically why an inductor and a capacitor work together to make a tank circuit, that the capacitor does exactly the opposite. The low frequencies, it's got a high reactance, high resistance, so it's kind of like open. Then when you switch to high frequencies, the reactance is small, so it acts like a short circuit. So the L and the C pretty much do the exact opposite. There's a whole symmetry here. Capacitors are storing energy in the electric field, the inductors store energy in the magnetic field. They're kind of like two sides of the same coin. Also remember that we looked at the phase of these. Resistance has no frequency dependence, so it has a completely real reactance. L, C had reactances that were 90 degrees different from the resistance, but in opposite directions. So what that means is that, remember, if you have an LCR circuit or an LC circuit, you can find a special point that minimizes the complex reactances, and overall that minimizes the resistance altogether. That happens when the inductive reactance and passive reactance are equal. So it's like having this vertical piece and this vertical piece down, start to affect each other out. So that's where the circuit is going to have the minimum in this resistance, and that's where it tends to want to operate at. So if you equate these two reactances, the inductor, this reactance was 2 pi times this critical frequency times inductance. The capacitor's reactance was 1 over 2 pi F naught C. So solve this for F naught. There's some critical frequency where L and C have minimum reactance. So this is what I want to think about as far as special frequency. Okay, so I'm going to build a super simple case. This is a switch, either be to the left or to the right. Here, when it's closed, it's connecting to one set of pole, one switch. Or if I put it to the right, it's only connecting these 2 lines. So this is a single pole. There's 2 different possible configurations, left to right, double row. So there's my inductor. capacitor. And there's my battery. This is a chain. The L and the C parallel, that's the chain. Chain like storage, chain not like. The way that this is going to work. First, I'm going to flip the switch to the right, which effectively takes the inductor out of the circuit. And all that's going to happen is my capacitor is going to charge up the same polarity that the battery has. Positive on the top, positive on the bottom. So charge the capacitor. Now, flip the switch to the left. And what you have in this simple circuit now on the left is just a charged capacitor and an inductor. This is like a battery and an inductor hooked up. So the capacitor will discharge. As it discharges, it's creating a current that's going through the inductor. Current in the coil creates a magnetic field. Current carrying wire creates a magnetic field. But this is a current that is not constant. So the current that the capacitor makes the IDT is not zero. Current is changing. It's changing with time as this capacitor discharges. So initially, it's a really big current, then it starts to take off. But what's going on with this inductor? It's building up a voltage on it that is proportional to the IDT. Faraday's law of induction. So this changing current is causing a voltage to develop on this inductor. When the capacitor is fully discharged, current is no longer, no more current. So the fully discharged capacitor then have a inductor that has a voltage developed across it. As soon as this current goes to zero, I don't have any more magnetic field in my inductor. That's the, sometimes when you read about this, talks about the collapse of magnetic field. That's what's going on here. So the magnetic field going is carrying, it's going to make this inductor discharge the capacitor, and capacitor charges back up. And that's going to happen back and forth and back and forth and back and forth. Capacitor charges up, discharges the inductor that effectively gives the inductor some voltage, and it will discharge that voltage back to the capacitor. The voltage on either one of those two guys will look like this. You would eventually die back out. So there would be enough dissipatable losses to the heat that you would eventually, the oscillations would quit. That's why to make an oscillator that has a continuous output, you need to, one, supply it with energy to minimize these losses. So that's the amplification part. And they need to supply the energy back to phase with this. That's the beat and phase part. So that's all the ingredients here that I need for an oscillator. But keep it from dying out. Can't give it too much energy back because it's like distorted. So there's like a perfect amount of energy that will just keep this thing. So the L and the C in parallel, that's like a energy storage. By putting in an LC tape circuit to a transistor amplifier, we can build sinusoidal oscillators, harmonic oscillators. So that's what we're going to do next. Questions so far?
Do you have a like a parent function for that kind of graph? Isn't it like e to the negative something?
For the charging and discharging?
Well, like for that bottom chart there, yeah.
Yeah, it would be yeah, it's it'd be a sine. Be a sine function with decaying exponential envelope. Something like that. So you're superimposing a regular sine wave and
Like something that decays, yeah.
yeah, so amplitude is a decaying exponential superimposed on the sine wave.
That makes sense. Okay, cool. Thank you.
And it's because you got this exponential here, that works great for the harmonic oscillator equation where you take two derivatives and you're back to where you started. That's nice having that.
That is nice.
So let's build oscillator. So I'm going to give you a circuit for a very rudimentary transistor oscillator that incorporates all those three ideas. There's my NPN transistor. So the basic stuff that we had for all of our transistor circuits.
So before we get like a little like too far along where this question is relevant, like how long are you looking at a tank circuit holding that like voltage output with no connection, like the once you flip the switch, like is that just depending on like efficiency for materials that you like how high quality your parts are for that circuit, or like size, like the size, like a big deal?
All of those would be work that. My guess is that you get probably 5 or 6 oscillations before that was completely flat out. They dissipate, like closing that switch to charge it and then flipping back to make it oscillate. You would die out. You would have to. You have to look at that on an oscilloscope to catch that. It would be faster than the oscillations. Decaying exponential.
So is there anything you could do to the decaying exponential to increase like, could you like decrease the decaying exponential to get it to flatten out? Or is that kind of what we're doing with the oscillator, what we built in the lab?
Yeah, so you have to either give it more energy to keep it going, or you can change the L and the C values. Those would also affect the decay, but that would also affect the oscillations too. So there's not much you can do with that other than use it as the frequency generating seed for the amplifier. Did that?
Yeah, that's good.
Okay, so 2 resistors divides the base. And emitter resistor and emitter capacitor, just like before. And the purpose of these guys, and the reason you see them on almost all transistor amplifiers, is for 2 basic reasons. Really, is one. This pair helps to stabilize this base bias. This is typically our ground. Here. Having a little bit of resistance between emitter and ground makes my emitter voltage here a little bit higher voltage than the ground. So it floats everything above ground. So it gives us a little bit more room to play with. But some of this emitter current gets fed back to the base. So there is some negative feedback here in the base bias, which is good. That negative feedback gives you some stability. What's bad though is if you have an oscillating signal being negatively fed back here, that decreases the stability. So what we want to do is only let DC bias feedback. So putting this bypass capacitor here essentially provides a DC path around this resistor that effectively grounds out the high frequency signal instead of feedback. So that's normally how we would set this up. So that's our transistor amplifier. To turn it into an oscillator, I need the tank circuit there. So this would be to the PCC. So this is going to give me this frequency where it's got one particular frequency where it's got a low reactance. Now I'm going to feedback, try to do some positive feedback of this signal to the space. In addition to keeping this bias here. So the way that this is done, a simple way, is by taking this vector here, my L and my C in this equation, and actually making this a transform. So two coils next to each other. So whatever signal goes to L, it induces the exact same signal in L1. So I'm going to give my R R1 and R2 for biasing. Through L and L1, I'm coupling back some signal. So this gives me positive feedback at the same frequency in phase, the base, and I still maintain my regular phase biasing. This would oscillate at this frequency. The problem with that makes sense. I've got positive feedback in phase with transformer. King circuit is going to provide a seed oscillator and a little bit of positive feedback for me. The main issue as to why this isn't a practical device is it needs a transformer to work. And that's typically a bulkier, large component. So we want to find a way to get this two-phase coupled signal back to the base without using that transformer. So there's a lot of ways that we can do this, and I just want to give you the two probably most common types of oscillators. They use a LC tape. So the first is called the Hartley oscillator, and the second is called the Colpitts oscillator. So Hartley oscillator. So an NPN transistor, just like before. R1 and R2 properly bias it. This stuff on the emitter, there's always now I've got to figure out how I'm going to feedback this signal into this. So that's not a junction, but that's two wires just crossing. So no node there. So I'm going to feedback the collector output to the input of the base. But I want to do that through a tank circuit. And for the Hartley oscillator, the tank circuit, capacitor, and an inductor. That's going to this base input. So I'm going to feedback the collector output through this LC tank circuit back into the base. So that's going to give me my positive feedback. And then there's my PCC power supply. We're going to do one more thing with this. So my L and my C, this is special inductor that is center tap. So it's a long coil of wire. And right in the middle is another leg of the wire coming off. And that's going to ground. What I effectively make here is one inductor in series with a second inductor. And I'm taking output at the middle. That's a voltage divider. It's a voltage divider built up of two inductors. The fact that I make the center of the inductor ground, it's kind of like I have L1, L2. These are like the two inductors that are using a signal from one onto the other. But since they're grounded in the middle, L2 will be 180 degrees out of phase from L1. So this is L1, L2. L2 is off by 30 degrees by L1. And that's not good because we want to feedback our signal exactly in phase. So my feedback phase angle would be 0 degrees, 60. It can definitely be 180. I can't feedback the out of phase. I have to feedback the in phase. But lucky for us, this 180 degree phase shift here. Remember, when I take the output from the collector to base, there's a 180 degree phase shift here. So there's one inversion, there's a second inversion. So that's no phase shift at all. So transistor throws you out of phase by 180 degrees. The inductor throws you off by another 180 degrees. But together, that's 360 degrees total. So you're just turn around 360 degrees and walk away. That's what we did. So the Hartley oscillator will give you a sinusoidal output at this frequency. The LC circuit provides the oscillating frequency. Coupling it back from the collector terminal along with the center tap here takes care of the phase shift. So I get a positive feedback in the phase. That's everything I need for a stable oscillator. That makes sense. Hartley oscillator is good for radio frequencies and higher. It is so like greater than kilohertz frequencies. It's not good for really low frequencies, like audio frequencies. And the reason is to get to low frequencies, your inductor, low frequency inductor is physically quite large. So these Hartley pulpits are both high frequency also. Okay, are you ready to make a pulpits? The Colpitts is minor modifications to the Hartley. Remember this: center tapped inductor and a regular capacitor. What's the easiest variation you could do on that Hartley oscillator? Well, don't center tap inductor. Center tap capacitor. Like that. This. Sorry. Two capacitors rounded at the center. Regular old inductor. So Colpitts is just the Hartley oscillator, but L and the C take on different roles in that I have effectively the equivalent of a center tap capacitor. So before in the Hartley oscillator, we had a inductive voltage divider. Now we have a passive voltage divider. We got 180-degree phase shift from here. These two capacitors, when they're tapped in the middle like that, they're like opposite polarities. Get another 180 phase shift, and those two again add up to. So Hartley and Colpitts are very similar. Invented about the same time in the 1920s for radios. That's in radio transmission. We started. So these were radio frequency oscillators designed for early radio stuff. Colpitts has the same drawback to Hartley in that it's only good for high frequencies. Audio frequencies, these aren't good at all. Benefit to the Colpitts over the Hartley is that the vector is a little bit simpler, it's just one. these are surprisingly easy oscillators to make. We can make inductors by just taking a piece of wire and wrap it around a pencil. Sometimes that's enough of oil to build a decent voltage oscillator.
So it feels like every single time back in the day when somebody came up with something, somebody else did like the opposite of what they did. And so then they get to have their own thing. Or like it's like that with everything. Like this right
Yes.
here.
Yeah, to this day, yeah.
Like they just do it like I wouldn't say opposite, but it's not really opposite. It's just like they flip something over and they call it their own. So then forever and ever they're gonna be like, well, you've got the full bits in the other one.
Yeah, that's how science goes, and especially when you are at the beginning of a new field where there's a lot of low-hanging fruit. It's not like this is really complicated. You have to go from partly to full bits. It's not a big change. So, yeah, there's all of these have people's names on it, like. On the Hartley oscillator. I think if you put a variable capacitor in it, it's a different name. It's a clap oscillator. One tiny clap. The clap oscillator is a tiny variation. And yeah. Well, I think a lot of these ended up being active, and I think that's why they have names.
Well, that's what I've realized is like being in like physics, like going all the way through. Like in every single class, there's either a formula or an equation that's like, I mean, like it's like flip 180, and then it's like all the different things, but like it does the same thing.
A lot of it's
Low hanging fruit is a good way to put it though. Like back then, all of this was very new, and so like super simple things could be figured out, and people take credit for them. Whereas now it's like almost common sense for somebody that has knowledge in the field.
yeah,
So
yeah, low hanging fruits. You didn't get to the phase shift oscillator. That one doesn't have a good name on it, so I don't know what happened. So we'll talk about the RC phase shift oscillator next time in the 5, 5, 5. That'll do. There'd be multiplied. So that's pretty useful. So that's coming up on Wednesday. Question? All right.
Thanks, Dr. Hicks.